In this video, we will learn about 2D equilibrium of a particle and how to draw free body diagrams. This is theory portion of the video, and we will look at the topics 3.1 to 3.3 from chapter 3. Chapter 3, Equilibrium of a particle, the free body diagram and coplanar force systems. For this part of the video, we will focus on two-dimension system only. We will learn how to draw free body diagram and how to apply equations of equilibrium to solve a two-dimension problem. Tug of war. There are two teams A and B, and there are two cables which are attached at this joint. Let's call this joint O. Now, if as a result of applying the forces by both the teams, if point O does not move at all, then we can say that the point O is in equilibrium. And when that's the case, we can say that the force applied by team A in this direction is same as force applied by team B in this direction. We know that the force is a vector, so we can write this as force Fa, which is the total force applied by all the three members of team A, is equal to force Fb, which is total force applied by all the members of team B. And as a result, we can say that force A plus force B is equal to 0, which is the resultant force of two forces, and this is called equation of equilibrium. So if point O doesn't move, then both teams are applying the same force, and that results this for the system in equilibrium. So now, to understand it better, we have isolated only joint from the surrounding, and we have indicated both the force by vectors, and this diagram is called free body diagram. It's called free body because we have isolated the body of interest, which is the joint, from its surrounding, and we have indicated all the forces that are being applied. And this vector representation explains here that resultant force, which is addition of these two forces, is 0. So for example, if one team is applying, let's say 100 or 1000 Newton force in one direction, then the second team is also applying 1000 Newton force, but in the opposite direction. So 1000 minus 1000 is 0. Now let's extend this idea and apply it to two dimension. So instead of, now consider there are four members, and consider the XY coordinate system which is parallel to the ground, and these four members are A, B, C, and D, and O is the joint which is also located at the origin of the coordinate system. If we draw the free body diagram for joint O, then that will look like as shown in the slide. And if the point O is not moving, then sum of all the forces acting at point O is 0. That means vector solution Fa, Fb, Fc, and Fd, if we write each force as a Cartesian vector and add them together, we will get 0 magnitude for the resultant force. However, resultant force can also be written as the components of the force along horizontal axis and vertical axis. So resultant force is here separated into x and y. And the equations of, then we get two more equations here. These are scalar equations. So this is vector solution, and in the scalar solution, we only consider one of the axes. So sum of forces along x-axis only is 0, and sum of all the forces acting along y-axis is 0. And these two equations are called our equations of equilibrium. We can call them EOE shortly. And because there are two equations, we can solve up to two unknowns. Remember that in mathematics, we need to have same number of equations, at least same number of equations as number of unknowns. So if we have three unknowns, we need three equations. If we have two unknowns, we need two equations. What does it mean that in the scalar solution, that each force, we can find out the projection of that force along x? If you know this angle theta, we can say that Fa cosine theta is the x component, and Fa sine theta will be y component of the force. So this is Fax and this is Fay, and we apply that same concept to all the remaining forces, and if we add all the forces x components, then that will add up to 0. If we add all the forces y component, then we get 0. And again, these are equations of equilibrium. So when a particle is in equilibrium, the sum of forces acting on it equal to 0. And that's why this is called equilibrium. It's not moving. For a frictionless pulley and cable, tension in the cable are related to T1 is equal to T2 when we do not consider friction. Later, when we consider friction, then T1 is not equal to T2. Let's look at few applications of equations of equilibrium. So the crane is lifting a load. To decide if the straps holding the load to the crane hook will fail, you need to know the forces in the straps. How would you find those forces? And the answer is to draw a free body diagram and apply equations of equilibrium. For a spool of given weight, how would you find the forces in the cable AB and AC? If designing a spreader bar like the one being used here, you need to know the forces to make sure ringing doesn't fail. And for that, we draw a free body diagram, simplified diagram by drawing only hook A and indicating all the forces that are being applied. So this is force in cable AB, this is force in cable AC, and this is force in cable AD. And then using equations of equilibrium, we can solve for the unknown forces. And this is one more application for boat attached to the bridle cables, and we can apply equations of equilibrium to know the forces within the cable, which is useful for sizing the cable. Coplanar force system. So coplanar forces are those forces which are only in one plane. So that's only in two-dimension plane. For example, everything here is in only one plane, XY plane only. So in this example, a cylinder C is attached to hook A through a cable, and then hook A is supported at joints B and D using cables AB and AD. So if we would like to know the forces in these cables AB and AD required to support the weight of the cylinder, which can be calculated simply by multiplying the mass of the cylinder with gravitational acceleration. So 40 multiplied by 9.81, that's the weight which is acting downward on the cable. We would like to know what are the forces into other two cables, and that we can calculate by drawing a free body diagram. So free body diagrams are one of the most important things for you to know how to draw and use for statics and other engineering courses. What is it? It's a drawing that shows all external forces acting on the particle. These external forces include the weight force, any tension forces in the cable, spring force if spring is available in the system, normal force if the particle is being supported, or any externally applied force acting on the particle. And once we indicate all the forces on the free body diagram, the next step is to apply equations of equilibrium to solve for unknowns. And how do we do that? So there are certain steps that we need to follow. Step number one is to isolate the particle or cut it free from its surrounding. That's what we have done here for point A. So all the forces that act on the particle, so force in cable AB, force in cable AD, and force in cable AC. Now, these are the cables, and cable always support the tension load. So when we draw a hook, the force is always going away from the hook, not towards the hook. And then identify the known forces. So for example, here the known force is the weight of the cylinder, which is 40 multiplied by 9.81, and the unknown forces are FB and FD. So we have two unknown forces here in this equation, in this particular free body diagram. And that means we can apply two equations of equilibrium to solve for them using sum of forces. So we can apply sum of forces in x equal to 0 and y equal to 0 and solve for FB and FD. Sum of forces in x direction equal to 0, and this is our direction assumption. We are assuming that anything that is going right is positive. So force acting on right is positive for horizontal axis, and there are two horizontal forces. Force in D, which is negative because it's going left, look at the direction, and force of cable B is at an angle to x-axis, so we need to find the projection of that force along x-axis by applying FB cosine theta, which is 30 degree here, and that is equal to 0. Now, second equation is sum of forces along vertical direction, so force going up or acting up is positive. So a sigma Fy equal to Fb sine 30, vertical component of this force by projecting it, and then there is another force which is acting down, and that's negative 392.4 Fc is equal to 0. There is no contribution of Fd along vertical direction because it only acts along horizontal direction. Similar to that, there is no contribution of Fc along horizontal direction because it acts only along vertical direction. And using the equations of equilibrium, we can solve for these unknown forces. Now, what are the other forces that we consider? So one of that force is spring force. So for spring, L0 is the original length of the spring when this external force was not applied. When someone pulls the spring changes the length to L. So spring has the deformation of S, which is change in final length minus original length. And spring force applied by the spring is opposite to the applied force, which will act in the upward direction, F spring, that will be is equal to K, which is spring deformation multiplied by, spring constant multiplied by deformation of the spring. Another force is the cable tension forces in the cable. So T1 is equal to T2 when we do not consider friction. So tension in the cable is same when the friction is not a factor. Third, if a particle or an object is it rests on the smooth surface, then the object has the weight which acts in the downward direction in the free body diagram, but the support applies the normal force to rest the object on it, and then there is this tension force T in the cable. So there are three more forces in this free body diagram: normal force, weight force, and tension force of the cord. And in the next video, we will learn how to apply free body diagram and equations of equilibrium concept for problem solving, such as one shown in the figure.